to do is look at the heating value of fuel, and this is the energy released, and let's look at the definition of the heating value. H sub RT is equal to H sub P minus H sub R at 298. So the products and the reactants are at 298. And so there's no delta H. So there aren't any delta H terms that we have to deal with. And so, and of course these are listed in a table, but before we get to the table, let's do an example with octane. And so we'll have C8H18 plus O2 yields 8 CO2 plus 9 H2O. I don't have to worry about balancing this with air because since everything's at 298, the enthalpy of elements is 0 at 298, and there's no delta H term. So I have 8 plus 4.5, 12.5. And now what I want to do is find the enthalpy H sub R. So H sub R is equal to H sub F bar 0 of the octane. And so that's equal to minus 250, 102 kilojoules per kilogram mole. And H sub R, we have two terms, or H sub P, we have two terms. H sub P is equal to 8 times the enthalpy of formation of the carbon dioxide, 393,757, with the CO2, plus 9 times minus 286,010 minus 241. So a question occurs if you look, this is for your water. And you'll notice that I have an enthalpy of formation. There are two different numbers for it. And so one number is the higher heating value that assumes the water condensed, so you get the latent heat. This one assumes that it's a vapor. So this assumes it's a liquid, and you have to decide, at room temperature, is the water vapor going to be a liquid? Is water going to be a liquid, or is water going to be this? Most often we use this, and this, if I use this number, it's called the higher heating value when I use that. And so if I do this, so anyway, we have higher and lower heating value. H sub RP, depending on water being liquid or vapor. So I have to just, so you decide. So it's a higher heating value. If it's a liquid, it's a lower heating value. If it's a vapor, most often we use the higher heating value. So if we do this, we're going to get the following. So I have that H sub P is equal to 5.72, 724 times 10 to the 6, should be a minus 10 to the 6 kilojoules per kilogram mole. And I have that H sub P minus H sub R is equal to minus 5.474 times 10 to the 6. And H sub RP is H sub P minus H sub R, I'm not going to keep writing the number out, divided by the molecular weight of the fuel. So in this case, the molecular weight is 114.23, where I get that the heating value is minus 47920 kilojoules per kilogram. And so what happens is there's a minus sign, and it simply reflects that the heat is leaving the combustion chamber. So the energy associated with burning a unit mass of octane is this amount of energy, assuming a higher heating value, and that's what we have. So, but it's listed as a minus. In table C3, lists the heating value, so we can do that. And for homework, do 1239, 1241, 1245. And this is the first law part of chemical reactions. There's a second law part, and with the part of the second law is we look at dissociation. And when I look at those problems, which you can read about in the text, I end up with double trial and error problems, which is a lot of work to do. So it's interesting, but conceptually for our course, so conceptually what I want to do is talk about the effect of dissociation. Dissociation of products. And what happens is, it's an endothermic reaction. And so, for instance, I might have CO2 going to CO plus O or something like that. And so what happens is the temperature is high, it drives the reaction backwards. And so I need to account for that. So as the higher the temperature, it causes dissociation of this. And so then my product term, rather than being those nice little CO2s, we end up with other products, and these become very reactive. So any compound or an element, nitrogen will dissociate into N, and that's where we got the NOx's from. And so we have this. So the big idea coming out of dissociation reactions is that at the high temperatures, I get dissociation of the products of combustion. The dissociation, these are much more chemically active, and so they react. But to make this reaction happen, it takes energy, so to reduce the adiabatic flame temperature, reduce the energy availability that we want from the chemical process. So we want to be aware of that. So that's the effect of dissociation. But we are not going to do double trial and error problems in this course. If you want to try it, you can try it on your own.